Morning, people. I hope you're doing well, my delovelies. So, give a listen to this. Of course, it may contain science and music. Good for our brains, good for our souls, and now, good for our cells. In an upcoming issue of The Lancet, researchers were able to produce and implant in vivo cells that released insulin in response to music. But how and why and how? We know our body has cells that can respond to music. In the ear of hearing people are little hair cells that, when sound produces acoustic waves that travel into our ear, vibrate the bony ossicles in our middle ear. And while that bony ossicle doesn't know or care that it's vibrating, because most cells in our body don't care about that sort of thing, they don't change or do anything in response to physics happening around them. They don't really need to know or care themselves, but when the ossicle vibrates, that force translates to our cochlea's little hair cells, and those hair cells' whole job is to pick up these vibrations and react to them. When the hair cell vibrates, the mechanosensitive ion channel sends the signal to our auditory nerve, basically acting as an analog to digital converter where the digital is our nervous system. This is just one example of how our body cells sense the physics around them and why it isn't so weird that a cell could sense vibrations from music. We already have cells that do. That's their entire job. But what if it isn't a cell's entire job? Our cochlear hair cells' job is transducing the physics they send into auditory nerve-friendly messaging, but other cells in our bodies do much more complex things with their mechanical information. If you've ever heard about how skeletons of medieval longbowmen are asymmetrical due to years of pulling that super heavy bowstring, that's because our bone cells have mechanosensors too. But rather than just say, "Hey nerves, I got a message, pass it on," the way our cochlear hair cells do, our bone cells, our osteocytes, respond to that mechanical information by changing their gene expression. In the case of longbowmen, that means forming more bone in the places that experience more mechanical load so the skeleton can better withstand the force exerted on it. Lots of osteocytes in a particular place sense a lot of force. They signal, "Hey, make some more bone here, and don't be so quick to resort bone in this area until we're sure we have enough." And eventually, the mechanical load is evened out and you don't need any more bone there. So, not only do our cells sense physics, but they can respond to those physics in pretty nuanced ways. Now, the human pancreatic beta cell produces insulin, but they don't typically have this kind of mechanosensitivity. They typically rely on glucose signaling to regulate insulin production and release, which makes enough sense typically. But in some cases, such as type 1 diabetes, the body attacks its own insulin-producing cells in an autoimmune response. So you could have all the chemical signaling in the world, but not enough cells to respond to it. That's why people with type 1 diabetes have to get their insulin through injection or through external pumps, and this project is part of a design to make processes like that more convenient. Our researchers created transgenic pancreatic beta cells that don't respond to glucose, but instead have these piezo-type mechanosensitive ion channels, not unlike the ones in your cochlea. Using a special cell culture technique, so the cells couldn't just rotate freely in the culture medium and transmit away the vibrational force, scientists tested what decibel level and at what frequency these sensors would activate. The ones they used, about 3 seconds of music at speaking voice volume of 60 decibels, and at 50 to 100 bassy sort of frequencies, respectively. when the mechanosensitive ion channels open in response to the good vibrations, calcium ions flood into the cell, reversing the charge in the cell membrane so the insulin inside it flows out, releasing it. Et voila! A cell that previously couldn't release insulin in response to sound now does so. This isn't the first cell-based therapy to be released with an external trigger. Groups like these have cells that respond to light, to magnetic fields, electricity, heat, you name it. Thing is, those don't always make good triggers because you can't necessarily control those things in your environment. Imagine using a heat trigger in your implant when you may use a heating pad or get a fever. But you'd think sound isn't any better. What? Are you going to live in a silent room all the time? Are you going to get a hit of insulin every time someone shouts boo? Well, what activates these cells at 60 decibels in specialized cell culture condition isn't going to activate at 60 environmental decibels when it's implanted in your body. Scientists microencapsulated these cells and implanted them in type 1 diabetic mice. The microencapsulation creates a semi-permeable membrane that allows insulin to flow out, but doesn't allow immune cells to get at the implanted cells to search and destroy the way they do for natural insulin-producing cells in type 1 diabetes. And once they're in the animal's belly, the mouse's body is absorbing a lot of the vibrations from day-to-day sound. If it takes 60 decibels to activate the mechanosensitive ion channels when it's in a specially constructed dish, it's going to take a whole lot more vibration than to activate that same channel through the mouse's body. So, when tested, researchers couldn't get these channels to accidentally activate at random noises, even loud ones like lawnmowers or fire trucks or low-flying aircraft. The sound had to be relatively continuous for at least those 3 seconds to get the insulin flowing. They couldn't even get the insulin release going when playing music at a, quote, mouse disco, where the mice were moving around freely. The insulin only released from these mechanosensitive cells when the mouse's belly was on a speaker, getting maximum vibration into the mouse's body near the implantation site, and stimulating the mechanosensitive ion channel enough to activate and trigger the release. That means it's pretty hard to accidentally activate these cells, but pretty easy to deliberately activate them, which is exactly what you want from a trigger mechanism like this. And the resulting insulin release is pretty close to typical glucose trigger dynamics in normal human pancreatic cells. The result was that one 15-minute music session restored our implanted diabetic mice to normal wild-type blood insulin levels. And because it takes about 4 hours to build up a full supply of insulin inside these cells, you can't just spam music on your belly for infinite insulin. There's enough of a cooldown to avoid inappropriate insulin release, but not so much of a cooldown that you won't have enough insulin for your next meal. Overall, that means this mechanically sensitive trigger can approximate normal physiological insulin release with multiple safety checks to avoid unintentional release. Insulin is a natural payload for this delivery mechanism because it's made naturally by a cell, and a technique like this can work for all sorts of cell-based therapies. The insulin is a proof of concept, but these ideas can work in principle for a bunch of different biopharmaceuticals. Is it better and more reliable at this phase than an insulin pump? Nah, probably not. But it's an important early step toward a different paradigm of drug delivery. But I'll answer the question we're all thinking. What kind of music really got these cells going? Fortunate for us, we have a chart. Alas, classical music was not ideal to trigger mechanosensitive insulin release. I get it. We're not a bass-heavy genre. But you know what did well? The soundtrack to The Avengers, and definitely Queen's We Will Rock You. With that optimal musical stimulus, the cells released about 70% of insulin within 5 minutes and completely released its insulin within 15. You know, sometimes engineering is coming up with completely novel ideas. Sometimes it's taking existing ideas and mashing them up in a whole new way, like using nature's pre-existing vibration-sensitive cellular mechanisms to activate what's usually a chemical phenomenon. Yeah. I'd say that'd rock you.